So this morning, I'm going to spend the first few minutes talking about two bits of statistical engineering. Statistical engineering is what you do to try to make an algorithm run faster. And one of the advantages that I had with developing this algorithm is that I started in 1985. At that time, computations were costly. So I had to use tricks that were fast, basically approximations. So here last time we saw that here's a tree that predicts the type of drivetrain that a car has, whether it's a four-wheel drive car or front-wheel drive or rear-wheel drive car. And one of the variables, so I have 428 cars, some Toyotas, some Fords, and so forth. And I have, as predicted variables, obviously the make of the car, whether it's a Toyota or Ford or GM. And I have various other variables, like the price of the car. Let me go there. Right, I have the type of a car, whether it's an SUV, whether it's a wagon, whether it's a sedan, or whether it's a sports vehicle. The price of the car, retail price and dealer cost, engine size in liters, the capacity of this engine, number of cylinders, horsepower, city miles per gallon, highway miles per gallon, the weight of the car, the length of the wheelbase, length of the car, and the width of the car. So, I'm going to, this is like a toy example. I'm going to use this example to illustrate some of the problems of the so-called the naive approach, where you just do an exhaustive search. Make has 38 levels. There are 38 makes of cars. So, if you want to split the data on make, so that one subset of makes go to the left side of the tree and the complement goes to the right side. There are, like I highlighted in yellow, 2 to the power of 38 minus 1 possible splits. And how do you get that? Well, suppose you have now Toyota has the brand, the make, has to go to either left or right. So let it go to one side. When it goes to one side, there are 37 makes left. So it's 38 minus 1. And for each of these makes, there are two ways. Either they join Toyota or they don't join Toyota, right? So it's 2 to the power of 37. But you have to exclude the case where everybody joins Toyota and it's not a split. So it's minus 1. Okay? So it's an exponential number, and that number evaluates to 100 billion. We only have 428 points. At the root node itself, you have to spend 100 billion splits to evaluate the impurity of each of those splits. That's very expensive. Okay? And that's why it took our part, our version of CART, 36 hours to construct this tree, right? And that's because we have 38 makes, but if you add another make, so this data set was obtained from the year 2004, which is almost 18 years ago. The new cars for that model year. But since then, we have got a lot of new models like Tesla. So you add a Tesla there, just add one more data point, the time goes to 72 hours, which is ridiculous, right? So that this is just so expensive. And so way back in 1986, 87, I was trying to basically come up with a cheap, at that time, it was more for fun. It wasn't really for research. At that time, I was doing theoretical research, and I had a student, my very first PhD student, and maybe for you new PhD students, I'll give you a tip. It's not necessarily a good idea to work with a brand new assistant professor, because that guy doesn't have problems for you to solve. If there's a problem he or she can solve, that person will solve it for himself. Why should that person give it to you, right? So this student came to me, and it's not because she wanted to work with me. She didn't want to work with me. She went to the department chair to want to work with the department chair. The department chair said he was too busy, and he said, well, here's this young guy. He has no students yet. Why don't you ask him? So she was sent to me, and I was a brand new assistant professor. I can't say no. The head of the department told me to take these students, so I took her. After 6 months, she couldn't solve the problem I gave her because it was a problem that I myself solved as a PhD student. I eventually solved it 3 years later. I didn't expect her to solve it, but I had no other problems. I thought maybe she's smarter than me, so she couldn't solve it. But by that time, I was into teaching this class, and I started to have all these, realizations about the weaknesses, practical limitations, and so forth of this algorithm. And I thought I have some cheeky ways of shorting certain things. And I asked her, if she could program. Turns out that she was a wonderful programmer, the best programmer I've ever met, a student programmer. I mean, she would meet me at 8 o'clock in the morning. She woke up at 3 a.m., go home for a few hours of sleep, and then she would come and see me the next day at 8 a.m. and give me the output. At that time, the output is not on a laptop. Output is on fanfold computer paper. I mean, it's a whole stack of fanfold. I don't know whether you've seen fanfold. So we'll go through the things and we'll see, oh, okay, this doesn't work. Let's try this. It's like you have a dam in a wall with holes. We just plug in chewing gum or whatever, okay? So this is what I thought about this problem. So I thought, I mentioned this in the first class, that Fisher's linear discriminant analysis is really good most of the time and really fast. So my idea was to piggyback on linear discriminant analysis, right? Linear discriminant analysis will give you linear combination splits, but though they are not easy to interpret, so I wanted to mimic CART and have univariate splits. It's called univariate splits on one x at a time. And so I ended up thinking, well, why don't we do variable selection first? Choose the x, and then apply LDA, which is really nothing. It's just one dimension, right? So then when it came to this problem, right? So guide can save a lot of time by not searching for the best split on all the other variables. But if it finds that the best split is still on this variable, it still has to go through that 2 to the 38 minus 1 search to find the split. So in fact, guide actually found that, yeah, that variable is indeed the most predictive variable at that point at the root node. It still has to find that subset, right? So what do we do? Well, I decided to use LDA again. So at that time, it's like, I have nothing but LDA. That's my only tool. Okay. How do you apply LDA on categorical data? So if I do not have categorical variables, if I just have all those continuous variables, forget about type, say retail price, dealer cost, those are continuous variables, right? Then if you look at the data in the space of those continuous variables, so there is retail price 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? So now we have 11-dimensional space, x1 to x11. So imagine a galaxy in 11 dimensions. And there are 408 stars in this galaxy. But these stars each of them has one of 3 colors. The rear-wheel drive cars are in red. Those are red stars. The front-wheel drive are blue, and the four-wheel drive yellow, right? So we have 3 colors. So now imagine a night sky in 11 dimensions with 428 stars brightly shining in 3 colors. What LDA does is it tries to partition, because there are 3 colors, it tries to partition this 11-dimensional space into 3 polygons, okay? So that within each polygon, they're mostly red stars, and another polygon mostly yellow and so forth. That's what LDA does, all right? So now, and it does it very well, as long as they are not categorical variables, because we're talking about this Euclidean space. Now, when you have a categorical variable, what do we do with categorical variables in linear regression or logistic regression? We convert them to 0, 1 variables, dummy variables, right? So for each, so I have, imagine the data, I have a matrix like this. right? F of Y, which is the type of drivetrain, right? This is a four-wheel drive. This is a front-wheel drive. This is rear-wheel drive, four-wheel drive, and so forth, right? Then I have a make, right? So this is my X, right? So this may be a Toyota, this may be a Ford, this may be a Toyota, and so forth. Okay, well, I flashed out into 38 dummy variables. We call it Z1, Z2. Okay, so if it's Toyota, Z1 is 1, and all the rest are zeros. If it's a Ford, Z2 is 1, and all the rest are zeros. This is a Toyota again, right? And now I'm back in Euclidean space, okay? So I still have that 428 stars, but they're now in 38 dimensions in Z space, okay? So what I really want is to be able to convert. I want to linearly partially order. Actually, I want to totally order this variable, which is not ordered. I want to order it, okay? So now imagine you have 38 dimensional space in this galaxy, 428 stars of 3 colors. I want to find the best projection on the 1 dimension of these 38 dimensions. Okay. Actually, visually, you can project in 2 dimensions. It's like, now I send an astronaut to the galaxy. I give him a Polaroid camera or whatever camera. I say, you go up there in your spaceship, you fly around and give me the best image of the galaxy so that the stars separate as much as possible in terms of color. Okay. That direction in which the separation is maximum is called the first linear discriminant coordinate. The second linear discriminant coordinate is the axis orthogonal to the first, where you have the next best separation. How do we measure separation? Analysis of variance F test. Okay, analysis of variance F test. So it's like you have a space like that, and then the red stars are here, and there's a purple stars and the orange stars, right? So what's a good projection? I don't know, it's hard to, maybe this is not a very nice example. Let me draw a more obvious example. So here are my axes. Here's 1. There's another. Right? Now this projection is the best, right? Because the purple points will project here. The blue points will project here. And the red points will project here, right? Now look at those 3 shapes. That's where the means separate maximally. And the easiest way to measure that is the F ratio, right? If you project here, oops. You know, they'll all be overlapping each other. The red will be here. The blue will be here. And the purple will be here, right? So that's not as good. Okay, and that projection is just an eigen problem. There's no search. Okay, it's just a matrix operation. So it's very fast. And so once I project there, so imagine that there may be a Toyota car here, and then maybe a Ford here, and then maybe a Volkswagen here. There may still be a Toyota here because Toyotas make all kinds of cars, right? The red may be 4-wheel drive, the blue may be front wheel drive, and the purple is rear wheel drive, right? So I may have some Toyotas here. And I may even have a Ford here. I may have a Toyota here, right? Okay, so I project them down, and then I can, now what do I do? I'll show you an actual picture of this. So this is what it looks like. Okay, this is what the cameraman brings back. I couldn't overlay them together because they just overstrike too much. So they're basically like, if you look at the axis, the blue cars are a little bit more on the right. The red ones are the four-wheel drive. The red ones are more to the left. Right, so the greens are more in the center. So basically, I project them down, and then I replace. So this is my Z1. I replace them. I should not call them Z1. I'm sorry. Okay, I should call them Z1. Let me call them. Let me call it D1 for first discriminant coordinate. The second one is the one orthogonal to. Okay, so what I have now succeeded in doing is I've replaced this with D1. All I need is this column and this column. Right? All I need is the first column gives me the colors. The second column, the last column gives me the location along one dimension. And now I just search along D1, along the D1 line. It's almost like all my stars are no longer in 38 dimensions. They all drop down to one line. I still have 428 points. They still have 3 colors, but they're now on one line. It's a drastic approximation. I'm approximating 38 dimensions with 1 dimension, right? And you may laugh. You have not experienced LDA. LDA is really good, okay? And LDA does not require this cameraman to spend his whole lifetime flying around this galaxy to take a picture. It's an eigen problem, okay? You can find that line without searching, okay? So once I have that thing, so now I have all these points here, there are 428 points at different colors. I do a split here, I go one by one in between data points. All right, each time I do a cut, that's one subset of those cars, okay? And that's the result. And it turns out this subset, God must love me. This is exactly the subset you would do if you spend 36 hours. I'm not saying this is a theorem, okay? This serendipity. But it's serendipity supported by a very powerful technique. So I should say that nobody knows if the so-called perfect subset that I spent all the time to calculate using 36 hours of CPU time. Nobody knows whether that is the right subset because it's a random sample. Okay, so the point here is it is not necessary to seek out the so-called perfect solution because that perfect solution may not be perfect in the first place. It's a random sample, right? And nobody really knows what the perfect solution is. It is good to get close to the perfect solution. Then people may have faith in your method, right? What matters most is that if this split is not the same one, it's not the so-called perfect one, suppose it's the right one. Suppose I make some mistakes and the Toyota went to the wrong side. Well, I have another chance to correct it because I'm going to split it again on other variables, right? So that's a wonderful feature about recursive partitioning. You don't have to be right all the time. If you use linear discriminant analysis, it's a one-shot thing. You have to be right that time. There's no correction, no chance for correction. With a tree, you will split it again. So what is then more important is, or most important is, make sure the tree is the right size. You don't grow too big to get too close to the data and chase after noise. You don't stop splitting too early, right? Okay, so that brings us to pruning, how we prune the tree. So anyway, so this is a bit of statistical engineering, which I'm still pretty proud of. You know, people poo-poo for against linear discriminant analysis. It's like ancient, but you know, it allows you to save a lot of time to do more things, right? Okay, and I'll show you what more things we can do with this kind of time savings. So, okay, so here is a technical description of what I just told you, you know, in words or graphically. So, if there are only two classes, if there are only two colors, then you don't need this trick. Okay, so if there are only two colors, so you have Toyota, and there are two colors, is front wheel versus rear wheel drive. For Toyota, you find out how many of the Toyota makes or cars are front wheel drive. For each make, Honda, how many are front wheel drive? You know, Ford, how many are front wheel? Then you order the makes in terms of proportion of front wheel drive cars that they produce. And then you split along that. Okay, and there is a theorem there that says that if you do it that way, you will always get the same split as if you went through searching all the 2 to the power of 38 minus 1 splits. Okay, so for when there only, so capital J is number of classes, the number of colors of the stars. If there are only two colors, you can handle as many levels as you have. If you have more than two colors, like here, I purposely chose 3 types of cars: front wheel, rear wheel, and four wheel. So I have 3 colors. Then you cannot order them with proportions because it's not just one proportion when you have 3 colors, right? So I will do the exhaustive search, meaning I will search through all of them. If I have fewer than 11 or fewer, then the number C is the number of makes. Because 2 to the power of 11 minus 1 is 2 to the 10 is 1,000. No big deal. I can do a 2,000. I can do 1,000 splits if there are only up to 11 makes. Beyond that, then I do this using LDA, which is what I described to you. Okay, so visually it's like you send a cameraman into this space and he takes a picture so that on the horizontal axis of his picture, the colors separate as much as possible. Okay, and then you use the coordinate along that line as your numerical variable, just like you would use it for the weight of the car or miles per gallon. You use that, and then you split on that. Okay.
Question.
Yes.
So, I mean, it would still work if you just used it when C was less than 11.
Yes, yes, but this is approximate, right? So, I mean, so from the practical point of view, because I'm not just developing the algorithm, I'm writing software for people to use. If I still use this for C equals to 5, people say, you are just a cheapskate, you know, right? You know, why don't you try to get the best separation, right? So I do this only when it becomes, you know, intolerable. Okay, yes. Yeah.
Could you do the shortcut twice? So like group two of the categories together?
Oh yeah, yeah, you could do that too. But say consider yellow, but two of the colors say the same color versus that. Then you have one ordering, and then you do it 3 times, right? Red versus non-red, yellow versus non-yellow. And I remember I tried that, but it doesn't do better than this. Yeah. So if the number of colors is j, so there's j choose 2 computations, right? So if j is large, that can still be expensive. If there's j colors and number of colors is large. So Varun is suggesting you consider one color versus the other colors, and then it's like a 2-color kind of problem. Whereas even if j is large, do LDA is just, it doesn't really increase the computation too much. Yeah.
That's another question.
Yes.
This is fundamental misunderstanding or something, right? Couldn't you just, you're only using the largest description.
Right.
Here. Couldn't you just take the whole vector, just do the LDA thing, get the orthogonal with different coordinates, use those instead of.
Yeah, you use the D2 as well as D3.
You would just like chuck them all in there, treat your categorical thing as a numerical thing throughout the whole algorithm. I need to convert the dummy variables to one column, right? I mean, if you say include D2 and so forth, then may as well just stay with the Z's, right? I stay with the Z's, but still I can't, right? I can't get subsets. Right. Okay. There's no gain. Maybe just do D1 and D2 rather than set 1 of the set 38.
Yes. Yeah. I did try both, get the best subset using D1 and then use the best subset using D2, and I tried empirically on a few examples. D2 really did any better than just D1. But you raise a good point. So what I'm here talking about is statistical engineering, right? Just like for example, the iPhone or the Samsung phone, right? They do a lot of engineering there. They're not using the optimal components because then it becomes too expensive for people to buy, right? So they just replace things that they can replace so that the thing is still within reasonable cost and still works pretty well. And that means that you could have a startup tomorrow and try to compete with Apple, all right? And you might be able to beat them, but you may have a hard time beating them on price. If you want to beat them in terms of quality and speed, you may have a hard time beating them on price. Okay. So similarly, this algorithm that I talk about, any student who listens to my talks can come up with a different algorithm, right? And you can replace components and so forth. And so what I'm saying is not the last, the best way to do it, but it's just one way to do it. But one thing that's maybe I should mention is I always feel that in order to be a good applied statistician, you have to be a good theoretical statistician. Because you must have good theory, you must know enough theory to be able to apply the theory. Because most of the time, when you apply this, if it's novel, it will be applying an old theory. Nobody has applied it in this way before. Okay, so nobody has thought of using LDA in a recursive fashion. People think LDA is a one-shot thing, right? So I applied LDA in a recursive fashion, and then I applied LDA again on this sub-problem of reducing the number of computations from an exponential number to something that is just actually the number of computations here, the number of subsets is not n minus 1. N is the sample size. If you have 428 cars and each one has a different weight, then there are n minus 1 ways to cut on weight, the gaps, right? But here, the gaps are j minus 1. It's not n minus 1 anymore, right? Because it's just a number of colors. So, oh, sorry, not j. It's c, the number of makes. I only have 38 makes. Even though I have 428 cars, I only have 38 makes. Like Toyota makes a bunch of cars. Some of them are front wheel, some of them are four wheel, and so forth. So I'm just splitting on gaps between 38 numbers. So that's super fast.
That's another question.
Yes.
So you're using LDA a lot.
Yeah.
I guess you could do something marginally more complicated, like internalizing the LDA.
Yes, certainly.
Good idea, or does that not help?
That idea, you will suddenly lose to me on speed. Okay, anything you do more complex, you lose. The thing is, do you gain enough to sacrifice the speed to gain on accuracy? That, I think, is not dependent so much on what you do locally, but as a tree, as I mentioned, pruning. Okay, you can actually do something very sloppy, and you may have to grow a bigger tree to recover the accuracy, but the accuracy in the end, if you recover it correctly, maybe still be pretty good, right? So there's multiple things going on. So when I have research students working with me, they come up with all kinds of ideas like you just suggested. They're all wonderful ideas. But the thing is, does it pay in dividends, right? So, okay. So this in a nutshell is what the guide algorithm does. Starting with the root node, it recursively partitions the data to grow a very large tree. I call that T sub 0. So at each node, it will search for the best X variable to split the data. Okay. Whereas CAT will check every X variable, find the best split, and see which ones give you the maximal reduction in purity. So imagine if you have a genetic data set, right? In a genetic data set, it's not uncommon to have 500,000 X variables. If you use CAT, CAT will search over the 500,000 variables to find the optimal split on each of them. Whereas guide will not bother to find the optimal split on the variables that it doesn't select. It selects X first, okay? And how does it select X first? What is as old as LDA or even older? Chi-square test. Chi-square test, right? So I use a chi-square test to select X variable. So for example, here, why did guide split on make? It forms a chi-square table. Four-wheel drive, front-wheel drive, rear-wheel drive. Toyota, Ford. Just a guy does a chi-square table. All right. Now, if make of car is independent of the class variable of the Y variable, my Y variable is the three colors, right? Then the chi-square will not be significant, right? So how fast is that? Well, you know, I could do it when I was an undergraduate student when we don't even have pocket calculators. Okay, it's just arithmetic. Okay, if you have a variable like a cylinder, number of cylinders, okay, guide will do is that you could have them have one column to be cylinder 1, cylinder 2, and so forth. But if you have other things like city miles per gallon, what guide does is just cut up the range of city miles per gallon values into the quartiles and form a 3x4 table. Okay, right? And people may you can talk about whether it should be 4x3 or not 3x4 or 3x5 or 3x2. But the thing is that in recursive partitioning, unlike most of theoretical statistics, in most of theoretical statistics, you know, n goes to infinity. Here, as you split, n goes to 0. All right. So you might be able to divide the range of city miles per gallon into more than 4 ranges for intervals, but then eventually you don't have enough data, so you may as well stay. And there's another reason I'll talk about later, why I convert the continuous variable into a sort of discretized variable to form a chi-square table, right? I'll get to that soon.
Can I ask, so you're using a chi-square test, which is asymptotic with value. You're saying that n goes to 0.
Yeah.
So should you use something that's finite sample value?
Actually, I have a paper in 1989 in Annals of Statistics that shows that the chi-square approximation for the chi-square table is not uniform. So when I was a student, PhD student in Berkeley, every few years, there'll be some papers published in the statistics literature about the continuity correction. I don't know if you heard about the continuity correction. in the continue. You see, nowadays you don't hear about it anymore. When I was a student, that was like a hot area because people were doing simulations on the accuracy of the chi-square approximation. And some simulations show that without that correction, it's not so good. With the correction, it's better. And some people will find the opposite. Okay, so here's a continuity correction. In the chi-square test, you have the observed minus the expected. Right? That's the chi-square statistic. Right? You have the cells, and then you find the expected values under the independence hypothesis. The continuity corrected chi-square goes like this. Okay, so you stick in a little half. Okay, and there are lots of papers on this, and people are fighting. I mean, really, respectable statisticians fighting. Why do they find this out? Because as n goes to infinity, this goes to this some whatever chi-square distribution, right? This convergence is defined. There are nuisance parameters. The nuisance parameters are the marginal probabilities of the table. And I proved the paper, which nobody seems to care. And for good reason, because if they care about that, they cannot use the chi-square test. Because the size of any hypothesis test right is the infimum or minimum of the probability of type 1 error. Right? So you say that I have a test with size point of 5%. That means, it's a maximum. It's a maximum. Okay, this is over the so this is a theoretical issue given H naught, right? The maximum is over H naught, right? H naught, independence hypothesis, rows and columns are independent, but the table has got unknown parameters. So this is the margins, right? So pi 1 dot pi 2. Oh, sorry. Should be pi dot 1, pi dot 2. Say n. Right? So the null hypothesis is that pi j is pi. Right? That's the independence hypothesis. So the supremum is over all margins. Okay? Now I proved that paper in the paper 1989 paper that supremum is 1 for any alpha. For any sample size, forget about n going to infinity. It's already 1, which means that whatever alpha you use for a chi-square test is quite meaningless. It depends on how weird your table is. Okay, so you say something that reminded me about this. You were saying that these chi-squares go to the thing, but they go.
But I guess you could use a permutation test.
Oh, yeah. Some people do that. Yeah, that will be a way to get around it, but that will be
Slow.
yeah, it will be very slow. Yeah, you can't afford to do that. Yeah, so the thing is, are you willing to wait 36 hours before you get a result because you want the perfect one, right? So
I guess your point is just you want to remove ones that are sure.
Yeah.
Matter.
Yeah.
You get something that maybe matters.
Yeah. Actually, I have another way to fix this problem. It's non-uniform thing. And that one has to do with, okay, let me go on first, and then I'll tell you how I fix this problem. Okay. So anyway, you know, you understand what this is, right? So basically, you do that, and oh, sorry, this is the split, right? Just a split, and then you prune it. So you get a sequence. You keep growing until you get T0, and then you prune it back. So this is just a root node, right? So little t stands for node, but if it's itself as a generic tree, I put parentheses around it to indicate that it's a generic tree with only one node. Otherwise, without a parenthesis, T naught refers to a node of a tree. Okay. So then we use cross-validation to try to evaluate. So basically, we want to choose. So now we go from variable selection to tree selection. Okay, we have this huge tree that we grow until maybe everything is pure, so no point to grow anymore. And then we start snipping. Right? Every time we snip, we have a different model. Right? From an grossly overfitted model to a grossly underfitted model when you prune everything. Okay, so now it's model selection. Actually, even this question is not so simple if you think about it. How do you prune a bush in your garden? There's no prescribed way. Do you prune the left side first, then the right side first? Well, your left is my right, right? So now for this thing that I mentioned, actually the card people solved it, which is I think the biggest contribution to this field is how to prune this. Okay, like how do you go for a haircut? How does a barber cut your hair? You see, so pruning a tree is like cutting a hair. You make a mistake, you cannot put the hair back, right? And you don't want, when you prune the tree, you don't want to consider all sub-trees because that will be a massive computational problem. So you rather have a sort of a nested sequence, so at least the computations are manageable, right? Ideally, you want to say, I want the best sub-tree. I don't care. I can wait 1,000 years. Oh yeah, you wait. By the time it comes out, you're dead. Nobody cares about the result. Okay, so, all right. So let me talk about the chi-square test here. Okay, so this is what happened to the COVID data, the first example I had. So COVID data had the age category, and the y variable is die or survive. So here's a chi-square where the columns, the rows are the y value, it's just a 0, 1. The columns are the x values, and if x is an ordered variable, guide will sort of group them into intervals so that you get a good size number of observations. So age category 1 is has that many observations. These are the youngest group of people. Age category 3 to 4 are the oldest folks, right? So I just do a chi-square test and I get a p-value. And then I do Charlson score. You know, the Charlson score is a sort of a quantity, it's a numerical value. Basically, it counts how many comorbidities you have, although some comorbidities count 2 points, right? So like cancer counts for 2 points. So guide chose to cut it at just group into 2. There's an algorithm that decides how many. 0 means no comorbidities, 1 means 1, more than 1 means more than 1. So it gets a chi-square value, a p-value, right? And it goes on. So let me clean this up. So you may think, oh, the problem is solved, right? I just have to choose the variable with the most significant p-value, the smallest p-value. And that's the most significant variable, and that's the one I want to split the data, right? So yeah, this is renal disease. I order this in, most significant to least significant: dementia, myocardial infection, peripheral vascular disease, cerebral vascular disease, diabetes, cancer, and so forth. And this is one thing. If you're trying to choose the variable with the smallest p-value, they are all incredibly small. This is from R. You ask R to calculate this chi-square and get p-value, R will say this is smaller than 2.2 times 10 to the minus 16. R will silently tell you, don't ask me for more accuracy. This is 10 to the minus 16. Right? Why are the p-values so small? This is because there are 31,000 observations. 31,000 is not big. We can have millions of data. That's why when you have big data sets, everything is significant. Okay? Even though the true effect is tiny, but the sample size is so big, everything is significant. So how do I choose which variable? Now I get something that is not 10 to the minus 16. Right? So now you have another engineering problem to solve. Right? You could say that all these are 10 to the minus 16. They're all equally good. I don't care. Maybe if I'm a true statistician, I don't know. I just toss a coin or throw a die or whatever. Right? But that's no good because that cannot be replicated. One of the, you may have noticed if you read the statistical journals in the last couple of years, there is a big revolt starting from psychology, where they don't believe in this p-value stuff because things cannot be replicated. You know, publications, the results in publications cannot be replicated, and so there's this big p-value thing. Anyway, I'm not going to talk about that. I can give another lecture on that thing. But so what do we do? We know that they're not equally insignificant. They're not. Right? So what do we do? Well, I have this 3 or 4 volume book. It's almost like an encyclopedia on distribution theory. That's what I always reach out to when I was a student. And nowadays, I reach out to Google. Okay, when I was a student, I reached out these 3 volumes, and so there's in each volume they talk about each distribution. And in one volume, there's a massive chapter on the normal distribution. It has a collection of all the properties of the normal distribution, approximations for moments, approximations for probabilities, all kinds of things. And I found in the chi-square chapter, there's a reference paper by 2 mathematicians, Wilson and Hilferty. That is way back before, no, maybe, yeah, 1931, before I was born. Before I was born. I was born in 1951. So this is way before you guys were born. What did Wilson and Hilferty do? They published a math journal. At that time, the chi-square test was already developed, right? Pearson already developed. Showed that asymptotically, this chi-square statistic converges to a chi-square distribution. But at that time, there were no chi-square tables. So it's like, at that time, the iPhone was developed, but there are no cell towers. Okay, so you have a technique that says asymptotically converges this distribution, but there are no tables. There are only normal tables. What Wilson and Hilferty found is a very simple mathematical approximation that converts a chi-square quantile to a normal quantile, so you can look it up in a normal table. Isn't that wonderful? They are not finding the p-value in this extreme table of chi-square and use the p-value to go back to the normal table to see what is the normal quantile that corresponds to this tiny p-value. No, they are bypassing that kind of, this tiny tail area. They somehow just have this thing. So when I found it, I was jubilant. Okay, and then I turned it around. I use it both ways, backward and forward. So they were just converting. The formula was converting a chi-square to a standard normal. Then I use it backwards to convert back to a chi-square 1, so that now every chi-square table has its equivalent of chi-square 1 value. Okay. So this is a 2 by 3 table, so it has 2 degrees of freedom. When I use a Wilson Hilferty, the equivalent chi-square for 1 degree of freedom chi-square is 1936. This one is a chi-square 1 already because it's a 2x2 table. So the Wilson-Hilbert is 1505. There's no need to, I shouldn't say Wilson-Hilbert, there's no need to convert. This also is 2x2. So most of these are already chi-square 1. Well, this one is not. Oops. Right? This is a 2x6 table, 6 raised columns. So the degrees of freedom is 2 minus 1 times 6 minus 1 is 5, 181. I use that Wilson-Hilbert, I get 145. So you see, I'm dealing now with reasonable numbers. I'm not dealing with super tiny numbers, 10 to the minus 16. I'm not dealing with 10 to the 16. Okay, I'm just dealing with ordinary numbers. So if you look at them, and that's how these tables were ordered. This is the largest, and that's how Guy chose that variable to split. Okay. So now, I'm not saying that the Wilson-Hilbert approximation is super accurate. It is not, but it's good enough. And if it is not accurate, I may accidentally choose H cat instead of Charleson's score, but they are both super good, right? They're both super good. It's like I have two arms, and if I'm ambidextrous, you don't let me use my right hand, I can use my right hand, right? Okay, and nobody will ever know. The good thing with statistics is a lot of times nobody ever knows because you do something wrong, nobody knows because nobody knows the truth. All you can say is that in my lifetime, I used the 5% alpha. So 5% of the time I'm wrong. Okay, but you can say when I was wrong. Right? But of course, this 5% assumes that the convergence is uniform, which that's another story. Okay, so that's how Guy gets his part of the reason why he gets his speed. Right? So if you are interested in the formula, I sort of use it 2 ways and juggle it up. So it's very simple, right? So you give me a chi-square from a chi-square table, 2x5 table or whatever, and you tell me the degrees of freedom from that table. The table will tell you the degrees of freedom. You just plug it in here and plug it in here, all right? And then you calculate 3 numbers, W1, W2, and then you use this formula. And then magically, it gives you this. So the W is the chi-square 1 degree of freedom quantile that is approximately equivalent to the X, which is chi-square new degrees of freedom quantile, without looking at tail areas. Oh, I'm out of time. Sorry, I digress so much. I'm out of time. So maybe sometime you guys should maybe raise a flag. And Varun maybe raise a flag. Okay, so yeah, we'll continue on Wednesday. All right. Thanks.